Today, going to look at how to solve empirical formula problems, which is it's going to be they're kind of lengthy process, but once you get the hang of how to do the process, it's very kind of replicable and shouldn't be too difficult. So first, here we got a definition. It's a chemical formula representing the lowest whole number ratio of the number of moles of elements in a compound. So the lowest whole number ratio, one, that means something like ethane would not be an empirical formula because you could have a lower ratio of CH3. So if you did an empirical formula problem with numbers representing ethane, the answer you would get would be CH3. The fact that some moles is going to be a key factor when we're doing the conversion part of the problem, and we'll see how we get a lowest whole number ratio as part of this process. Okay, so first thing we're going to do is we're going to make a 4x2, 4 columns, 2 row table, one for each element in the problem. So I'm going to do insert table 4x2. I like having everything center justified. I think it looks a little bit better. And so there's one table, there's a second, and a third. Because in example 1, we've got sodium, we got sulfur, we got oxygen, 3 elements. So next, if we're given percentages, which remember percentages are mass percentages, we're going to just rewrite or type the percentages as grams, and they're going to be our kind of starting value for each of these tables. So 32.38 grams, 22.63 grams, 44.99 grams. And I'm going to put the symbol for each element in the bottom left, this box that we don't usually utilize, just so I help keep everything straight. And so now we're going to convert each of these gram amounts into moles, because an empirical formula is the lowest whole number ratio of moles. So put grams at the bottom for each because we started with grams in each table. Remember, I don't have it on this sheet, but from our conversion factor, anytime we're dealing with moles, the number that goes with it is 1 mole. If you don't remember that, then look back at the mole conversions unit notes. Grams is going to be the molar mass for each element that we have here. So this is going to be nice with converting the molar masses because you don't need to add anything up. It's going to be all individual elements. One important note that we see here with oxygen is that normally if we are just talking about oxygen, we have to factor in that oxygen is diatomic, and so its molar mass will be 32. But here we are talking about oxygen within a compound. And of course, that is oxygen is not necessarily diatomic then. So just the mass of 1 oxygen. So that's normal mole conversion stuff. Now we'll do calculator things now. And when we find these mole amounts, you're going to want to keep more decimal places than usual. You're going to want to round it off to at least 3 or 4 decimal places each time. I'll do 5 there because I don't want to round it. 49 up to 50, and I already typed it. Okay, so we get our mole amounts, and we can put our units. They're not really going to, units are not going to be nearly as important for this, because ultimately our answer is going to be a chemical formula, like NaCl or H2O that doesn't have units. All right, so we get our different mole amounts, but these are very much not whole numbers. So the way we're going to get a whole number ratio is we're going to look at our moles. We're going to pick the smallest of these guys. So here the smallest one's 0.70498. And we're going to divide each of these by the smallest of them. So that's obviously 1. 1.4078 divided by 0.70498. So you get 1.9969. And $3.9886. Oops. All right, so now after we've done that, if each divided amount for a ratio is within 0.1 of a whole number, then we're going to be able to round these values to the nearest whole number. So that's within 0.1 of 2. And that's within 0.1 of 4, rounding up. That's obviously 1. So our ratio of moles is 2 to 1 to 4. So now for our answer, we'll take those values and they become the subscripts in our formula. Na2, since the 2 is with sodium, Na. S, which we won't put a number with because we don't write subscripts of 1 in a formula. And then O4. So our answer is Na2SO4. So one more example, which shows what to do with one kind of different situation. It's going to start the same. We'll insert, this time only 2 tables, because if we read, containing only phosphorus and oxygen, so just 2 elements. Oops. So I'll go ahead and identify the boxes P and O. Here we won't need to change any percentages to grams. We're just outright given grams. So phosphorus is 4.433 grams. Oxygen we'll have to do a little bit of math for, because it doesn't give us the oxygen, it gives us the total. Of course, we can find the oxygen by subtracting out the other part, the phosphorus. So 5.717 grams. So now remember, we'll convert each of these gram amounts into moles. So 1 mole on top always, the molar mass of the element on the bottom. So we get 0.143 moles, and we get, not 4 point, and we get 0.3573 moles. Once we get our moles, to get a ratio, we're going to divide both of them by the smaller amount, which here would be the 0.143. So that's obviously 1. And with the oxygen, we get 2.4986. So that is not within 0.1 of a whole number, so we're not going to be able to round that off. What that would round off to is 2.5. Now, of course, we can't have a formula, oops, wrong spot, of PO 2.5. We need whole numbers. So now, if you ever get this where one of your divided numbers rounds not to a whole number but to something 0.5, we're going to multiply both of them by 2. I'll just put that in that very bottom box. So now we can have a ratio of 2 to 5, which is mathematically the same ratio. So you need to make sure to multiply both of them by 2, not just the 0.5 one, but both of them. We keep mathematically the same ratio, but now with whole numbers. So our answer is P205. And so that is the kind of drawn out process, but the process of finding the empirical formula of a compound when you're given either mass percentages or just masses of the elements within the compound.